Okay, let's go into chapter 3. So chapter 3 will focus on crystal structure. We'll learn about how to draw or how to calculate something related to unit cell. Then you will look at crystal structure for metal, then another structure that you see on the screen. Okay. For this chapter 3, we will see a loss of time. We will see this structure. Okay, this is called unit cell. So we try to fit in atoms and do analysis inside this cube. Okay, all right. So what you will learn in chapter 3, you will learn what is the definition for crystalline, what mean by non-crystalline. Okay, what mean by crystalline, what mean by non-crystalline, and how to identify basic building blocks for solids, right? How solid is formed. And then this is the atomic structure, crystal structure for solid material. So again, this number 3 here is important for your assessment, for your test or final exam. Okay, and you should able to, based on your calculation, you should able to identify or what kind of crystal structure you have. Then so on and so on, and so on. For this module, I do not go into X-ray diffraction method. Means you don't need to look at the graph and predict the element in the sample. Okay, so this one you don't need unless you take material science or something. Okay, let's look at crystalline structure from introduction. So some name that not familiar for mechanical engineer. For example, celestite, they look like this. Pyrite look like this. Amethyst look like this. But if you go to those crystal shop, then you familiar lah, almost like look like this lah. Okay, I like NaCl. So this is actually is salt, but it can be crystallized in and form something like this. Okay, this one is the you see this one in the volcano area, then you see something like this. Okay, this chapter will look inside how all this shape come from. Why the object look something like this? Where you see all these small crystal like this? Why this crystal form like this? Okay. So definition for crystalline is that they are arranged in a certain pattern. Means you see a pattern, and they form a solid, have a long range order. Then they are called crystalline. Means you can say they are more similar like polymer, but we are now looking at solid. So there's a pattern, arrangement pattern, and they have a long range order. Means they're able to repeat a very long. So when they repeat very long, then they see the same similar shape already. Okay, so for example, you have a cube size of a crystal cell. So when this pattern repeat in the long cell, you'll see a rectangular shape crystal. Okay. So crystalline solid, normally they are, example is metals, alloy, and ceramic materials. Right. So in chapter 1, you learn about type of material, you learn about metals, you learn about ceramic. So some of it that they are short range order. For example, water, we have a very short range order. Although water is H2O, H2O, but they are separate. molecule and molecule, right? So that's the definition, crystalline structure. Crystalline, when you talk about crystalline material, means you have a certain pattern and it can repeat. It's like a Lego bricks like that. Okay. First technical drawing or sketch is called lattice or space lattice. So it's like a template when you want to do analysis for material. So this is an example of space lattice. So it's an atomic arrangement. Yeah, okay, atomic arrangement, how the atom being arranged in a certain way. So if it's a crystalline, means you can use this space lattice to do analysis because it's repeated and you can fix them inside the cube here. Okay. So this is the parameter when we use analysis. So you will see this is a unit cell showing lattice constant. So when you have a cube, in material science, we don't use the word cube, but we use lattice or unit cell. Okay, so you have A, B, C, and you have atoms on four corners. Later you'll see atom inside and outside also. But this is a simple cubic, and you have an angle alpha, beta, and gamma. So this one will form the shape of that crystal. Okay, so they are vector, lattice vector. So in this chapter 3, since you've seen the word vector, so you need to recall what is vector. So there's a dot product, cross product, and so on. So the length and so on. So this is called ABC, is called axial length. Then the angle is called interaxial angle. Because of this interaxial angle. See, so it is not necessarily straight, but it will form by a certain angle. So certain angle, if you change the angle, this alpha, beta, and the length of this ABC, then it form into certain category of lattice or crystal structure. Later there's there's a long table to refer. Okay, your job is to find maybe A, B, and C or alpha, gamma, beta, or by giving you alpha, beta, gamma, you look at the table, or this is what and what, then you use that certain formula to solve. Okay, so this is the table that I'm saying just now. So if you know the A, B, C, alpha, beta, gamma, then you will have a cubic system, tetragonal, orthorhombic, and so on. Okay, what is important is that you know that there's a table that you can refer. What you differentiate from each crystal system is the A, B, C, alpha, beta, and gamma. When you change all these parameters, the 6 parameters, it will form each individual different crystal system. Okay, and we will learn space lattice. We will learn simple cubic. Because it's simple, we won't ask you in the test or exam because it's too simple. Right? So simple cubic means this is a simple cubic. We have how many atoms at this corner? You have 1 atom at this corner. So number of atom, later we'll learn about wording. So this is called simple cubic. Means you have 8 atoms that form along the corners. This is called simple cubic. And the angle is 90 degrees. Okay, it's fall under cubic crystal system. ABC, simple cubic means this one almost same, right? Or scalable or in linear way. So all these ABC is the same. You see this one ABC same, so the length is same. Then later we will learn body-centered cubic. We will learn face-centered cubic. The rest a bit complex, we won't go inside there. Okay, unless you are in the material science, then yes, we'll go into there. Okay, but for mechanical student, it's important you know that what is crystal system, what affect the crystal system, and then what is the how many space lattice you have. There are a lot, but you'll learn some of it. Simple cubic, we won't use because it's a simple. We will go into body-centered cubic. Later, you will see short form for body-centered cubic we name as BCC. F-centered cubic we'll use FCC. And there's one more HCP, not here. Okay, so again, this one you can see in my slides. Okay. So these are another example of translation from this table into diagram form. So is categorized, I help you to categorize. We have 4 big family actually. We have cube family, hexagonal, and so on. Okay. So based on the shape and orientation, you'll fall under each category. So we will learn about these 4 basic type of unit cell. Simple, we already tell you what is simple, is the one that I draw on the whiteboard here. We will start to learn what is BCC, FCC, and this base-centered. Okay, we will learn this one. Okay. Important is, okay, this slide is important, and also is the main thing of this chapter 3. So on the left, this is simple cubic. This is body-centered. What is body-centered? There is an atom in the middle of the cube. You have 4 molecule on the top, 4 atoms or particles, 4 atoms top and below, and the center, there's 1 atom at the center. It's called body-centered. Another one is called face-centered. Face-centered means in the cube, how many face you have? 6, 6 or 8? 6, So face-centered means the atom go to the face. You see, each face have 1 atom, each face have 1 atom, each face have 1, and then the back, bottom, left. Okay, so this is how you differentiate. And popular question will ask you this one and this one. Later you'll learn one more, but we will focus on body-centered, BCC, face-centered, FCC. Then there are lots of there are some calculation to calculate about this cubic system. Okay, so this is a simplified diagram. This is forget the terms already. There are 2 ways of representing a unit cell or lattice system. You can either draw like this, or you can draw like this. There are 2 ways of presentation. What else? Okay, example of a simple cubic is your salt NaCl. Okay, then this one, BCC and FCC is metal. It's metal. So there's a table also to refer what type of metal have what type of crystal structure. Okay, first one, we will learn these 3. This 3 is the main component in your assessment. We will be asked about BCC, body-centered cubic, face cubic. Again, face cubic means there's one extra atom at the face, at the center of the face. You have 6 faces. Huh? Then there's one more, hexagonal close pack, HCP. You'll see a hexagon on top and bottom, and it form a crystal structure, something like this that you see on the screen. So what is HCP? How HCP form? You have 6 corner. This one, I think this one means one atom here. So you have 1, 2, 3, 4, 5, 6, 7. Here also same, top and bottom same. But what is different is in the middle of HCP, we have 3 atoms at the center of the body. We have 3 atoms packed at the center of the body. Okay, so this is how you draw the crystal structure and unit cell. Yeah, so this is important. You need to know how to draw this one. Okay, normally in section A of the question. Okay, then you use this one to do analysis. Yeah, so don't miss. If you are being asked to draw BCC, for example, don't miss out the atom at the other faces. If you lazy to draw this one at the back one, then it's wrong. It's not a BCC. Okay, normally student will miss the one at the back, the one at the left, and one on the bottom. They will draw front, top, left, right. Then they miss another 3. Then they get the wrong marks. Okay, so this you need to draw the full one. HCP a bit complex. Not fair to ask you in final exam because you won't have sufficient time if I ask you about analysis on HCP. So this one won't come out in this one won't come out in final exam, but remaining 2, yes. Yeah. Okay, so this one read lah. This one is HCP. So you know that when you have more atoms, you have more dense. Means density will increase. Okay, this one you read lah. Okay, we start with the first type. We call BCC. So BCC is you have one atom at the center of the cubic. So how many atoms you have inside this cube? How many atoms you have in the unit cell? Top 4, bottom 4, middle 1, 9. So remember when you draw BCC, 4 at the top, 4 at the bottom, and 1 at the center. You don't need to draw this dot line. But we want to see whether you know how to illustrate a BCC. Okay. So if you're given some parameter, the cube side, this one, the cube side, one cube is 0.8, for example, only 0.8, 0.28 nanometer. So in 1 meter means if you take 1 mm, 1 mm, 1 mm volume of that particular metals, how many unit cell that you can form in 1 mm, 1 mm, 1 mm volume? Okay, or in 1 mm volume. So this one is only this, when you take 1 mm divided by 0.8 nanometer, it's just that at one side here, this one side here alone will have 3.4 million unit cell. Okay. Then the distance between the atoms, between this one and this one, you check with an analysis called X-ray diffraction analysis. There's a machine called X-ray diffraction analysis machine, usually in the material science lab. Means you put that metals inside, you cut very, very small. There's a procedure preparing the sample. Then it's like a X-ray. You go inside there, then there's a ray that shooting at the surface. Then there's a receiver, then you see spike in the graph. You'll see something like this when you come out from the machine. So each one of these will tell you the energy of that particular spike. That one may be carbon, this one may be fluorine, and so on. Okay. I'm not sure whether we have this machine, but you can find out lah. Huh? Okay. I'll give you a video so that you understand, and when you see one, you know that is a X-ray diffractor machine. Okay, so this is an X-ray diffraction machine. What important is that you can identify, oh, this is the machine called X-ray powder diffractor machine. When you visit somebody lab, then you look at the shape, the structure of the machine, then you know, oh, this is a X-ray powder diffractor. So there's a so there's a graph come out. The spike will tell you the type of the material. Okay, so this one you'll see something, this raw material. So the spike will tell you the element. Okay, so they will calibrate the spike with the sample. They refer, what is this? Then they tell you what is this. This one very expensive, a few million for one machine like that. Okay, so this table will list out. You'll see this table in your test and final exam. So you see metals and lattice constant A and radius. So it tell you that, for example, this material, the lattice constant A. What is lattice constant A? Is this one. This is called A, and so on. This is lattice constant. And because it's a simple cubic, we know that simple cubic, A equal to B equal to C. So all these are the same. Okay, so you have A, and then you have atomic radius. Atomic radius is this one, I enlarge this one. This is atomic radius, R. Okay, so each one of it have one value. This table is important when you do analysis. When you see this table, normally in the at the back of the question, or sometimes if you're so kind, we'll just put under the question. So the constant value A we won't give, means we won't mention in the question, but you can find in the table. It won't be so direct like other module. Other module will give you the value, but in this module, you'll be given lots of table you need to refer. Okay, So there's a table. What is important for this slide is that there is a table for you to refer for A value and R value. This one, this is the R value. Okay, so then sometime how this table come in, either you use the value to analyze, or you find the A value, you go to this table, then identify what is this material. You calculate, let's say you calculate, then you find 0.330 for your A. Then from this table is this one, tantalum. This material, the A is near to this value, 0.330 nanometer, nanometer, then the answer is tantalum, for example. Okay. So this table, don't refer to the wrong one. This table is for BCC crystal structure. This table is for BCC crystal structure, which is the one that I show on the slide here. You have 4 on the top, 4 on the bottom, and 1 in the middle. All these metals have BCC crystal structure. Okay. And bottom one is FCC structure. What is FCC? You have 1 extra atoms at each face. Then these are the example. Okay. Yeah. Okay. Another way of asking question is that if this table do not give you, then you might ask to give some example of element that have BCC and FCC. But I will give you the early tips lah. If this kind of question come up, means you need to memorize. Either you're given table to memorize, or you're given table and do other analysis. Okay. Normally 3 example. Okay. This one is the HCP. This table is for HCP, right? HCP structure and all this. So you have A, B, C, and R. So later I will tell you what is A, what is C, what is A to C ratio, and so on. We're focusing on, okay. And there's one more table. It combine all. And this one is not combine all, but it gives you the distribution of metals. Don't confuse, this table is popular when it comes to assessment. Don't confuse with the right-hand side and left-hand side. Okay, so sometimes you will confuse, like you only read one side and then you forget about this one. There's 2 rows of data here. One is on the left-hand side, one is on the right-hand side. So for example, aluminium is FCC. A is 0.143 nanometer. Then nickel or platinum, they are FCC and so on. So if this table was given, normally it asks you to do calculation, and then it asks you to predict the element. You find the A, and then you go to this table, you find which one is the closest one. Okay, although these two are very close, but have different crystal structure. Okay, let's go to the first type. First type, we have A, B, and C. There are 3 types of drawing. First one is atomic site unit cell. Normally, you will only need to draw this type. Hard sphere unit cell, this one, normally when you do your lab report. Isolated unit cell, also lab report. Okay, so this one normally in test because we want you to work very fast and there's a limited time. But this one you need to draw properly for your report, right? So there's a normally you will see the question will mention it very clearly. draw the atomic site unit cell for BCC, for FCC. So you need to draw something like this and not this. Okay. So B and C, normally we'll use C to do analysis compared to A. Normally we'll draft A first. Then after we draw A, we'll convert diagram A into isolated unit cell. For example, for BCC, you know that there is an atom in the middle. What you do is that all the atoms have the same size, same radius. So what you do, you convert, in the middle you have 1 atoms, and then 4 at the top, 4 at the back. So actually 1 atoms at the corner is only quarter of the atom. Makes sense? This is quarter atom. Quarter of the atom, you cut watermelon. It's form quarter. Like you pack watermelon, 5 watermelon, and then you chop into cube. You chop it into cube domain. Like you put in the freezer, then you chop lah. Chop with the same height, same this one. Then you will see this shape. You use this isolated unit cell for your analysis for section B of the question. This one normally section A. Okay. Okay, now for BCC, any question on the diagram? Okay, now. First, are you able to identify? Are you able to differentiate the type of the diagram? And then when you do isolated unit cell, are you able to visualize in unit cell? Actually, it look like that. Okay, for BCC. So when you go to isolate unit cell, inside unit cell, we in material science, we can say in one cell for BCC, there is a 2 atom per unit. Mean inside here, inside 1 unit cell, like 5 watermelon, you chop, then you combine again all the watermelon that you chop, you will see 2 watermelon. You will form 2 watermelon. Can you get the idea? Yeah, means you break this one, break this one, break this one, and then you combine. You'll get 1 atom, right? It's quarter. 4 side, 8 side. 4 at the top, 4 at the bottom. You combine, you get 1. Yeah. So chapter 3, if you are good in imagination, that is good. Normally, if you cannot imagine one, you go and buy tennis ball, and you form. Try to imagine how the object works. Anyone still cannot see why in one isolated unit cell you have 2 atoms? Anyone still you have a doubt on this one, this statement? Can I? Okay. So I already explained how to form 2 atoms. This is the calculation to calculate number of atoms. So you take, this is normally is the first step of calculation. You calculate number of atoms per unit cell. You look at the structure, and then 1 at the center plus the site. BCC don't have face, right? I mean, at the face, there's no atom, only at the center. So 1 complete at the center, and then at the corner, you have 8. So 1/8 times 8. Answer is 2 atoms. Okay, this one will cost you 2 marks for calculation. Okay, this is to prove that you have 2 atoms inside the unit cell. Okay, so in the larger cell or a clearer illustration, so A, you can draw like this. Again, it's a hard sphere unit cell. This is a reduced sphere, meaning you reduce the size. This is the, you see under microscope. This is called aggregated presentation, means you stack all the molecule together. And you take one of the lattice system out, you do analysis. Again, when you see this one, and you see repeated pattern, this is called crystalline structure. If you take this one out, you take this one out, you compare, there's a different, then it is not crystalline structure. Okay? All right. Now we want to derive the second equation for today, which is relate the relationship between the A and the R. We start with the BCC first. BCC have one set, FCC have one set, HCP have one set. So you start with this diagram. You draw a cube, and then atom at the center, then one terms at the corner, one at the corner. Let me start with this one. This one might be confusing to you. I will draw step by steps. We're going to prove all these parameters, this one, this one, this one, and this one. So when you draw center BCC, body centered cubic, you, okay, I use the diagram on the one. We will recall your mathematics trigonometry. We look at the diagonal section of the cube. So when you cut diagonal, I will draw the plane. So I will cut like this, or I will chop the object like this. This plane. Okay. Can you see the plane that I'm drawing? I'm drawing this plane. So when you chop like that from the top, you will see one atom at the center. You will see quarter atom at the corner, but no atom here because you chop like that. Agree? Okay, once you chop, what is the distance between the cube? Is A. Right? What is the atom radius? I use capital R, but some of it you can use small r. This is R. One complete atoms, how many R you have? One complete atom, how many R you have? 2. So total here to here, you have 4R. Okay? This is A. This is A. Okay? Now, you know that this is 4R. Okay, no. This is 4R. This is, okay, this is AA. Okay. Next one is this one. It is, want to find what is this? Okay. So again, trigonometry. You look at the bottom plate. This one. Bottom plate, you are seeing this one, right? You are seeing A. How to find this one? This is 90 degree. Trigonometry? Yes. X equal to square root a square plus a square. What you get? Square root 2a. Okay, or square root 2a square. Right? So your x here equal square root 2a. So here, square root 2a. Right? And you do calculation. So you combine the mathematics, the triangular, square root 2a, 4r, this is a. Okay, so this one, hold on, I haven't tell you the there's one thing I'm missing. Okay. So how do you find this one in A terms? Is this one. You use this diagram. This is, you know that this is 4R, right? You know this is 4R. But before you find 4R, let's say this is X. You have square root 2A, you have A. What is X, this one? Again, X equal square root A square plus square. Right? Here, A square plus this one, square root 2, you get 2, A square. At the end, you get 3A square root 2, so you get square root 3A. Agree? So here, 3x equal to 3 square root A 3. This one equal to this one, the one that you see on the screen. So square root 3A equal to 4R. You rearrange because you want to capture BCC parameter in A towards R. So for BCC, first equation, and this one you need to, can say memorize. It's like memorize gravity. For BCC, your A to R ratio is 4R square root 3. This is the first important equation for BCC, and you need to at least understand why this one, how this one come from. Okay. When it comes to final, you don't need to show the step that I write on the whiteboard, but at least you know for BCC straight away A equal to 4R square root 3. Okay, so if you do not believe, you can go to the table I showed you just now. You apply this formula. For example, BCC, this one. You apply, you take the R value, which is on the, oops, it is on the right of the table. So no, this one. This one. Okay. The one on the right, you take this one, 0.125, you put inside here. 4 times 0.125 divided by square root 3, you'll get 0.28 something. Okay, for BCC. Okay, so two important concept for BCC. How many atoms in one unit cell? 2. What is the ratio, or what is the relationship between A and R? Defined by A equal to 4R divided by square root 3. These two is important for this chapter. Okay, the rest step I already show. So next, is on the packing factor. Okay. In short form, it called APF, atomic packing factor. So you calculated by this formula. You take the volume of atoms in unit cell divided by volume of unit cell. Okay, by using this definition, the third point, the third important formula, APF equal volume of atoms in unit cell divided by unit cell. Number of atom inside there. Okay, so before we look at the answer, can you do for BCC, what is the value for, what is the APF value, constant value for BCC? How do you calculate sphere volume? Cube, right? Cube, okay. Okay, you put this one. How many atom you have in BCC, in the unit cell? How many atom you have? 2 times the volume, 4, 3 pi r cube. Again, unit cell. Unit cell, you have what? How you find the volume of unit cell? A. How you find volume? A cube. What is A again for BCC? Substitute inside here. Rearrange. Cancel the R. You get one value. No, you substitute this one in already. You square it. Then you get one number. The detail I won't go deep lah, but the concept is there. Okay, I'll show you there. Okay, so okay, you will get 68%. Okay, maybe I do a bit mathematics for you lah. Okay. Okay, A, P, F equal to volume, atom, volume, unit cell. For BCC, we have 2 atoms, so times 4, 3 pi r cube. Unit cell, A cube, so I just substitute lah. So A cube, A equal to, what already? I forget. 4r. A equal to 4r square root 3. So you substitute here. 4r cube square root 3 cube. On the top, you get 8, 3 pi r cube. Okay, then 4 multiplied 3. How many? Okay, you do the calculation. At the end, you get 0.66. Yeah. Okay. 4 power 3, you press calculator, out 6 square root 3 over 2. Okay, then you press calculator. There's a number of this one. This one divided by this one, you get one number. Then you cancel out the R. Wait, something wrong. Wait, wait. Oh, sorry, I make one mistake here. There is no, all right, mistake here. There's no 3 here for R. So here is 3. So you cancel the R lah. Cancel R pi, you divide, do calculator, you get 0.68. Okay, you press calculator lah, you find the value. Okay, so for BCC, APC fixed already. Third number for BCC, if you find APC, you find. At the end, you get 0.68. Then you know this element is BCC. Once you know BCC, you can calculate for A. You can calculate a lot of things. Make sense? Sense, huh? Okay. So why on the slide here I put in percentage? It's because I take this ratio multiply by 100%. Make sense? R, what is R? What is R? Radius of your molecule or atom. Just now I do the calculation. Just now derive how you get R, right? This one. This one. Okay. So this equation number 2, this one is trigonometry, mathematics, triangular. Okay. Yeah. Okay. We do one exercise, then we call it a day. So example number 1, it asks you to calculate atomic packing for BCC, assuming the atom is hard sphere. That actually is what we discussed just now. Okay. So you take APF, you take volume divided by volume. Then we do calculation. You unit cell with this one, volume atom this one. You take this one, divide this one, and you get 68. Okay. On the whiteboard, I skip the calculation part lah. But this is how you get the 0.8. Okay, FCC, I think we continue next lecture.